For this presentation, we're going to take a look at chapters 6 and 7. So these two chapters cover experimental design and normal distributions. Now, as far as chapter 6 goes, there's not a whole lot there of interest. I mean, I definitely want you to read chapter 6. You might try and do the multiple choice questions. But then you should be spending most of your time on chapter 7. So before attempting the quiz on this unit, definitely read chapters 6 and 7, and then do all the exercises in chapter 7. Go ahead and skip the case studies, and then pay particular attention to question number 25. It's going to be a little challenging, but I think after watching this video and taking a look at the chapter, you should be able to figure it out. And if you still don't get it, I will provide some help with that particular problem. Okay, so one thing that I think is pretty interesting in chapter 6 is they bring up a couple of topics that I want to talk about. First of all, a lot of it is, talks about the scientific method. I think most of you have had the scientific method in other classes, so we're not going to dwell on it in this class. But first of all, I would like to ask you, what is a hypothesis? Now, some of you are probably thinking, or some little voice in the back of your head is saying something like, a hypothesis is an educated guess, because that's what people hear a lot of times in like high school and even in some biology classes. I want you to erase that from your memory. A hypothesis is not an educated guess in science. Instead, what it is, it's a statement. It is a testable statement. So it's something like, the rain has not caused butterflies to grow larger. That is a hypothesis. That is testable. It is a statement. The key things about this are that it has to be testable. And as we're going to see, we're going to actually do a lot of hypothesis testing. We almost always start out with a statement called a null hypothesis that we try to disprove. So educated guess, this has nothing in it about being able to test it. That is one of the big flaws with that definition. So if you, for some reason, go on to teach biology classes in the future or any other science classes, please never tell your students that a hypothesis is an educated guess. Okay, now what I want to do is I want to talk about this little illustration over here, illustrating the differences between random and systematic errors. So obviously when we're designing experiments, we try and eliminate errors in any way that we can. But errors come in two forms. So they can just be random, like we have no control over them, or they can be systematic, meaning that, there's usually some problem with the instrumentation that always gives us a slightly higher or a slightly lower value than we're expecting. So if you'll take a look at these bullseyes for a minute, you can see the differences between these two errors illustrated. So like at this one at the top, as you can see, the shots, I guess, are very far from the bullseye, but there's no bias involved. They're just sort of, whoever's shooting this is just not very good at it. This person, on the other hand, who made these shots, they are really good at hitting a certain place, but they're far from the bullseye. So this would be a large random error, and here you have a large systematic error. Now, in this illustration, as you can see, you have both of those types of errors are far away from one another. Okay, now there are some other terms that have sort of the same meaning frequently. So precision and accuracy are a good example of this. You hear both of these terms and people get them mixed up all the time. Even scientists who should know better confuse these two terms. I will definitely be asking you about them. And another set of terms are reliability and validity. So I guess if you take a look at this illustration here, let's first talk about reliability and validity. You can see that reliability is sort of similar to like a systematic error. So you're always hitting in the same spot. So this is really, really reliable. It also happens to be valid, you see. Here, this is a reliable shooter. He's just missing the mark. So they're very reliable, but not valid. Here, this is valid. It's around the bullseye. It's just not very reliable, you see. Okay. So precision and accuracy work the same way. And precision is sort of like reliable. It is sort of like systematic. So this person is shooting very precisely. You see what I mean? And here he's not shooting very precisely, I suppose. And then this is accurate, right? It's just not very precise. This is both accurate and precise. Now, we use the terms precision and accuracy a lot in biology because we frequently use them to refer to measurements that we're taking. So let me give you an example. What you see in this picture, this is called a digital caliper. Now, maybe you've used this in one of your classes before. I use this almost every day when I'm taking measurements of the lizards that I study. So, for example, when I'm measuring the head width or the head length of a lizard, I usually use one of these digital calipers because it takes measurements to 0.45 millimeters. You see that? Whereas with a straight ruler, so this measurement, for example, if that was the width of the head of a lizard, it would be 22.45 millimeters. Now, if I tried to do that with just a ruler, yeah, I could maybe try and eyeball it, but a ruler is really only, is really only going to give us a measurement to 1 millimeter. So I wonder which of these two things is more precise. Like, would you say that this instrument is more precise than a ruler? Or is it more accurate than a ruler? Okay, so I'll give you a minute to think about that. And then I want to tell you what the correct answer is. So you might pause the tape, write something down. So answer this question. Are my measures of the head relatively more accurate or more precise than the snout vent length measures? Write down an answer. Okay. All right, now the correct answer is that they are more precise. So this is more precise. In fact, we have a problem with some of these digital calipers because occasionally they will have a short here. So if you roll this thing down all the way to the end, you still have something like 2 millimeters on here. That causes a systematic error in all the measurements. They're still very precise, but they're not accurate. You see the difference? So I will be asking you about the different uses of these terms on future quizzes and exams in this class. Be sure you know the difference between these pairs of terms. All right? Okay. Now, the rest of the time we're going to be talking about normal distributions. So what I have in these two figures over here are some examples of normal distributions. All right, so let's take a look at some of these. And in a minute, we're going to be using the calculators. All right, so some of the characteristics of a normal distribution. Now, most of you guys have probably been exposed to normal distributions before. You may remember that in the previous unit, in the sort of introduction to like probability distributions, I even showed you a normal distribution. Okay, so they're probably not too foreign to you. First of all, how would you answer this question? What is the relationship of the mean, the median, and the mode in each one of those graphs? Well, obviously they're equal to one another. And that's one characteristic of a normal distribution. You may remember these from the earlier chapters in the book, the first unit. These are all measures of central tendency. So like in a skewed distribution, median and mean are not equal to one another, but they are in a normal distribution. All right. How about the area under the curve? Well, remember, a normal distribution is just a probability distribution, like a binomial distribution, like a Poisson distribution, two you've studied before. So the area under the curve is 1, no matter what the shape is. The area under the curve is equal to 1, so it's a probability distribution. How is the shape of these distributions defined? Well, we can kind of compare these two. Notice they can be relatively wide, meaning they have a lot more variation. And they can have different means, you see that? And those are the two things that define the shape of the normal distribution. So the mean and the standard deviation. Remember, we use standard deviation as a way of quantifying variation. Okay, so comparing the red distribution to the blue distribution here, you could say the red one has a lower mean, but a higher standard deviation. See, it's more wide. Okay. All right, so we're going to use two different calculators in Lane's book called the normal and the inverse normal calculators. So I'll get out of this this PowerPoint for a minute and show you these. All right, I'm just going to make sure that my tape is still recording. Okay, looks like it is. All right, let's see here. Okay, so if you go to the list of calculators in Lane's book, you're going to find these. All right. So there's the normal distribution calculator and the inverse normal distribution calculator. So let's just take a look at the normal distribution calculator first and see how it works. With it, what you put in here is you put in a mean and a standard deviation, and then you can pick any number, that's on here, and then find out what the area under the curve is. So if we didn't have a nice calculator like this, to figure out the area under this curve, we'd have to do some calculus. Or, back in the old days, we used to look up these areas using tables, but now with these electronic calculators, all that's gone away. This course is much easier than it was when I took it. We didn't have things like this back in those days. Okay, all right, so let's see here. I think we're going to start out with that one. So let's see how we might use it. Now, this is the type of question you're going to see in the homework. All right, so let's see what we got here. So we have a normal distribution, has a mean of 5 millimeters, all right, and a standard deviation of 2, all right. What proportion of the distribution is above 3? So maybe that sounds a lot like some of the binomial problems you worked last time. Well, let's see how we'd solve that. I just jotted those numbers down, so I'll be sure I put them in here in the right spot. So we have the mean of 5, right? And then the standard deviation of 2, all right? And what we want is we want the area above 3. All right, so you put that in, and you hit recalculate. Well, there it is. So about 0.841, that's what we would put as our answer. So I guess you could say we're reporting all answers in this class to a precision, not an accuracy, but to a precision of 3 decimals. So 0.841 is how you would report the answer to that question. Okay, that's pretty easy, wouldn't you agree? All right, let's see where we were here. Okay, now let's see. A normal distribution has a mean of 120 and a variance of 100. 35% of the area is below what number? Okay, so on this one, let's take a look at it for a minute. Notice we've got something new in here. This tells us the percentage, and we want to know a number on the normal distribution, don't we? Okay, so let's see what we're going to need for that. All right. Now, the other thing we should look at is, notice we've got variance here, whereas with these calculators, they ask for standard deviation, so that's something else we got to be careful about. So if you look at this, notice there's nowhere to put in that 35%. That's because we need the other type of calculator. So if we go back to the calculators here, you can find the inverse normal distribution. So if you look at the inverse normal distribution, what it does is it allows us to put in an area, a mean, and a standard deviation. And then it'll tell us whether, what number corresponds to it. So for this question, remember we were interested in 35%, so we need to put in 0.35 here. All right. And then the mean was 120. Okay, and then you may remember the variance was 100, so we need standard deviation, CSD. So you take the square root of the variance to get the standard deviation, which is 10. All right. Okay, now we wanted below what number, didn't we? So you have to click below. All right. Always look at the graph and then look back at the question. See if this visual aid matches what the question is asking for. So we'll do that for this just for grins. A normal distribution has a mean of 120 and a variance of 100. 35% of the area is below what number? Okay. So that's below that number. All right, that's what this number is. So when you click below, it tells you what the number is that corresponds with that. This area over on this side, this is 35% of the entire distribution. Okay? That's how you use the inverse normal distribution. All right, pretty simple, right? Okay, so far so good. Okay, well, let's take a look at some other examples and some other questions that we might get with the normal distribution and the inverse normal distribution. Okay, so a normal distribution of test scores has a mean of 38 and a standard deviation of 6. Okay, so this is kind of an odd situation, but so let's say you're taking, this test has been designed and, probably doesn't go up to 100. I don't know, it's got a mean of 38. Standard deviation of 6. What we want to know is we want to find out who is in this 80th percentile. Okay, so everyone scoring at or above the 80th percentile gets placed in an advanced class. So we want to find out who the smart kids are and put them in some advanced class. What is the cutoff score to get into the advanced class? Okay, well, the first thing you might ask is, well, which of these two calculators do we need? Both of the calculators have got a mean and a standard deviation on it, but only one of them do we put in a percentage. And that's what we're talking about with a percentile, right? We're interested in the 80th percentile. So that's the inverse normal. So let's go back over here and take a look at it. All right, here it is. So we're going to be looking at the 80th percentile. So let's just go ahead and put 80 in there. All right, now let's put in our mean of 38. All right, and the standard deviation of 6. All right, let's see here. Now that would have been the default. I had it set up a little weird. So if we would have, if we would have, let's redo this just to be sure everybody sees what I'm trying to show you here. I want to be sure. So this one doesn't work, right? All right, let's go to the inverse normal. All right, now let's put in the information it asked for one more time. So we're interested in the 80th percentile. We have a mean of 38. All All right, and a standard deviation of 6. Okay, now we want to know who the students are in the 80th percentile because we're going to put them in an advanced class. Does that mean that a student has to get a score of 32.95 or more to go to the advanced class? Look at the graph and see if it matches the question. No, see, we're looking for the top, the top scorers, the people in the 80th percentile or greater than 80%. So we have to click this below button to make it look like that. There's the cutoff. So this is 80% of the distribution, and over here we have the 20%. So these are the top scoring students. So you have to think about what the question is asking you for. So the answer we need is 43.05. So a student would have to get a 43.05 or greater to get put in the advanced class. That would be the answer to this one. All right. So again, I chose this one on purpose because I knew that this particular calculator, its default is above, but you have to really think about what it's asking you to get the correct answer. Just keep this in mind when you're doing problems for this chapter. All right. Many of the problems in the homework, you've got to look at the effect of the calculators and then go back to the question, see if it's telling you or at least looks like what you're looking for. This is a nice thing about having these visual aids. All right, now what I want to do is talk about how the normal distribution differs from a binomial distribution. Okay, so if you look at this little illustration here, you can sort of see a binomial distribution with a normal distribution superimposed upon it. All right, so how does it differ? Well, you may remember when we were doing binomial distributions, we usually had counts of some sort, like numbers of successes or something. So we're almost always working with some sort of discrete data. With normal distributions, they're really useful when working with continuous data. Okay, you can use discrete data in normal distributions sometimes. It just depends. Like if I was working with counts of scales of lizards, for example, I could model that with a normal distribution, not a binomial distribution. Probabilities of exact scores. So you may remember when we were working with binomial distributions, I could say, well, how likely is it that we would get like 3 heads, right? And then we could find out what the area of this block is. But what if we're working with a normal distribution? What is the probability of getting exactly 6.5? So that's like in here somewhere, isn't it? Well, remember this is 6.5000000, all the zeros you can imagine. The probability of getting an exact score on a normal distribution is 0 because the area is almost infinitely small if you think about it. Okay. So how about an approximation? Like how close is this normal distribution to a binomial distribution? Like, how does sample size affect that? Well, let's see. This may be easier to show by playing around with a binomial distribution. So I'm actually going to do that by going back to the calculators here and pulling up a binomial distribution. All right. So first of all, the effect of sample size. So on this, you can see this is pretty close to a normal distribution with a small, small sample size and a pi of 0.5. Or probability of 0.5. Let's change this to 100 and see what happens. Wow, that's even closer, isn't it? I mean, if you looked at that graph, notice how it's kind of cutting off the distribution somewhat. Okay, so I think it's safe to say that with larger sample sizes, the fit or the approximation of a normal distribution to a binomial distribution is closer. All right. Now let's go back down to something kind of small. We'll just work with 7 for this. So how about with pi? What happens when we change pi? Well, when it's close to 0.5, notice that a normal distribution would fit pretty well. But if you get close to like a probability of 10%, then you've got some major skew there. Or if you go in the other direction, probability of 0.9, there again, lots of skew. You see that? A normal distribution is not going to approximate that because a normal distribution is never skewed. It is always symmetrical. Okay, so why am I telling you all this? Well, we're going to actually be doing some problems where they sound like a binomial problem. They are a binomial problem, but we're going to use a normal distribution to solve them. Okay, so you'll get to see why we do that in a little while. All right. Okay, so let's see what we have here. So a normal approximation or a normal distribution approximates a binomial distribution best when sample size increases. It's kind of like fill in the blank. Like if I was going to ask you this, I'd probably be like a multiple choice question. And probability approaches 0.5. And we saw that was because it becomes skewed when you go in the other directions. Like if you get closer to 0 or closer to 1, then the binomial distribution becomes skewed. Now here's another thing though. Look at this while we still got this here. Look what happens when I change the sample size. So it's still 0.9, right? But let's put something like 200 in there. Look at that. It's almost normal. I mean, it's no longer skewed. So these two things, they sort of counteract one another to some extent. You can have a really, skewed, or I guess we shouldn't say skewed, but a probability that's pretty far from 50-50 as long as you have a really large sample size and it's still more or less normal. Okay. All right. All right. So in a minute, we're going to see how we might approximate a binomial distribution using a normal distribution. The thing is, when will it work? Well, or this method, when will it work? Well, it's going to work if the binomial distribution is more or less shaped like a normal distribution. Now, we saw two things affect that. One is what's the sample size? Big sample sizes are better. And then we also saw the other thing that affects it is we need to be close to 0.5. Now, there's a rule of thumb that you need to know. This is it. Okay, so if you multiply the sample size times pi, if that's greater than 10, you're okay. But because it goes in both directions, like 0.9 or 0.1, you also have to multiply the sample size times 1 minus pi. As long as both of these things are greater than 10, the normal approximation is going to be pretty close. Okay, so we're going to see some examples of that in just a moment. All right, so let's take a look at this again here. All right, so notice that when we place a normal distribution over a binomial distribution, it cuts off pieces of it. Do you see that? Like you have this big chunk of 5 here that is outside of the curve. So if we're trying to use a normal distribution to approximate the binomial distribution, we need to account for these pieces that are cut off. Okay, the way we do that, so for example, let's think of a typical binomial problem. So if these were coin flips for a minute, I might ask you, what is the probability of getting between 1 and 5 coin flips? Well, if you do 1, you see if it was a normal distribution, we'd draw a line there. And then with 5, we would draw a line here. And we'd find the area between those two lines. But that would underestimate the binomial, wouldn't it? Because it would like leave off half of this. All right? So what do? What we do is we actually find the area from about 0.5 below to 0.5 above. So we would use 0.5 from here to 5.5 to here, and then that's going to get more of the blocks you see. And it's kind of like, even though this part of the block is cut off, there's a little space there where you could almost visualize that piece going in there. So the approximation is actually pretty close to what it's going to be. All right. Okay, so we're going to actually try this. So let's see. So if we want, yeah, that's the one I just went through. What if we wanted to get, values below 6? All right. We could use, let's see. Well, let's skip on. I'll let you guys play around with some of these in just a minute. Okay, let's do an actual example here. Okay, so here's a binomial problem. So normally, let's see, we want to know the probability of getting 17 to 13 heads on a 30 flips of a fair coin. That's a binomial problem. But we're going to use the normal distribution to approximate that. All right, well, first, let's just refresh our memory. How would we get that with the binomial distribution? Let's take a look at that, and maybe we'll even jot down what the answer is here. Okay, so we have 30 flips, right? 30 flips. We want to get this is a fair coin, so it's 50-50. All right, no skew there. That's pretty normal looking. Nice. We want to know the probability of getting between 7 and, what was it again? Yeah, 13. Between 7 and 13. All right. Now, if I said nothing about doing a normal distribution, you'd use the binomial calculator. That's the answer right there. That's the best answer you could possibly get. So now what we're going to do is we're going to use that normal calculator to do this. All right. So remember, what we've got to do is we've got to cut off a little above and a little below, so that, because if we superimpose it, we're going to be cutting off pieces of this. All right. So what do we do? Okay. First of all, we might ask the question, well, is it safe to use a normal distribution? So this is when we go back to that rule of thumb. Remember, two things have to be true. N times pi has to be greater than 10, and 1 minus pi times n has got to be greater than 10. So in this case, n times pi is 0.5, right? And 1 minus pi is also 0.5, so it makes it a little easier. All right. So we take 30 times 0.5, that's 15. All right. Notice that these are both greater than 10. So, okay, we can do this. We should get a pretty close answer. All right, so what do we do? Well, remember, with the normal distribution, we need a standard deviation. All right. And we also need a mean. Okay. So you probably remember from the binomial chapter that to get the mean of the binomial distribution is just n times pi, so that's 15. And then the standard deviation is the square root of n times pi times 1 minus pi. In this case, I've already worked that out. It's that number. Okay, so then we use the normal calculator to find areas between a little bit below and a little bit above what we were doing here. So we need 6.5, not 7, and 13.5. All right, let's see how we're going to do that. So rather than plug all that in the calculator again, I'm just going to copy this. All right, and we're going to model this now with our normal distribution. Okay, so let's go up here to the normal distribution. All right. So remember, we found the mean of this particular binomial distribution, right, was 15. Okay, so we'll put that in. And then the standard deviation, so you'd use that formula. And then you would, from your calculator, you would copy it and then paste it in here so you don't have rounding errors. We've got to always avoid those. Now, we want the area between. Now remember, we need to be a little below, so we're interested in 17 to 13. So in that case, we have to put 6.5 because of the way it cuts it off, and 13.5. A little bit above, a little bit below. All right. That's it. And that actually is fairly similar. Now let's see what we got here. You may remember, if you remember or jotted down what I had from the binomial experiment, that's actually really close. So the answer is really close to what we got there. All right. Okay, so here we go. I put that into the PowerPoint. So the answer is 0.291. So this is using the normal approximation of the binomial. This is the answer you would get for this question. All right. And comparing it to the binomial, this is a good way you can check yourself, see if you did it right. You can look and see if you get almost the same one. Okay. All right. Could we have used a normal approximation of the binomial if we had used an unfair coin? So this coin is really tricky. It only turns up heads 10% of the time in 30 flips. Well, you would use that same rule of thumb we talked about. So we'd take pi times n and 1 minus pi times n. So 0.9 times 30, that's a lot, that's fine. But 0.1 times 30, that's 3, which is much less than 10, so no. Now, what I think you might try and do, try and go through all those steps we just did and see what answers you get. So first work this problem using the binomial approach, and then work this problem using the normal approximation. So the normal approximation is going to give you a probability of 0.016, or you would round off to 0.17. But the binomial is really different. See, it's like almost doubled what you got with the normal approximation. So the answers are quite different. Now, here's an important thing. So in this chapter, just because Lane wants you to practice and I want you to practice using these two approaches, you're going to be told to use a normal approximation. However, in future chapters, if you have a problem that looks like it's a binomial problem, you should be using a binomial calculator to do it, or a binomial distribution to solve the problem. It is always the best thing to use if you're dealing with data that can be modeled using a binomial calculator. And you're going to be tricked. So watch for it in a future chapter. I don't think it's this one. I think it's one of the ones coming up. But there's going to be some problems. And you're going to like work them using a normal calculator. And then you're going to look at Lane's guide, and it's going to say, you only get half credit if you did this, because it was actually a binomial problem. So watch out for that. Okay. All right. One final topic, and then we'll close this video out. So the standard normal distribution. When you open these calculators, all right, so like with the inverse normal calculator, do you see how this has a mean of 0 and a standard deviation of 1? That is the standard normal distribution. And that's also the default with the normal distribution. That's the standard normal distribution. Mean of 0, standard deviation of 1. So the values on the x-axis, you can see some of them are negative and some of them are positive. So in this chapter, Lane's going to tell you about how, back in the day, we used to use these tables, and maybe you've done this in other statistics classes, where you would sort of find these critical values using the standard normal distribution. We don't have to do that to work a lot of these problems, but we will need to understand how to do that for some future applications. Okay, so we need to at least know how to use the standard normal distribution, and to solve some of the problems in the homework, especially number 25, you're going to have to understand this relationship. Okay, so the standard normal distribution, as we saw, has a mean of 0 and a standard deviation of 1. Now, any normal distribution can be transformed into a standard normal distribution using this relationship. So These numbers you see on a standard normal distribution, like these -3, -2, -1, 1, 2, 3, etc., what those are called z-scores. Now, if this was some other type of distribution, right, like 57 and standard deviation of, I don't know, 7, yeah, okay. Now the numbers are totally different. We would just call these x-scores if you like, but we could figure out what z-score would be equivalent to these using this relationship, and that's what this formula does for us. All right. So a value from any normal distribution, so any x value on the x-axis, can be transformed into a z-score, all right, on a normal distribution using this formula. All right, so you just take the x-score minus the mean of that distribution divided by its standard deviation. All right, so let's look at an example of this. So we have a normal distribution has a mean of 50 and a standard deviation of 5. What value on the standard normal distribution equals 40 on this 45 on this normal distribution? Well, let's take a look at it. So what we've got here then is a distribution with a mean of 50 and a standard deviation of 5. Maybe these are like butterfly wings or something like that, some kind of measurement. And we want to know the area below 45. Let's just see what that is. Okay. So the probability there, as you can see, is about 0.158, or that area there. What would this be on a standard normal distribution? Okay. Well, the way we would find it, we would use that formula. All right, so let's take a look at what the formula does for us. So we would plug in our values here. So 45, that goes for x, and the mean is 50. Got to watch the sign here, divided by a standard deviation of 5. So notice the z-score is -1. Now watch this. Okay, so we're going to just switch calculators here. Whoa, we don't want to do that one. Okay, let's see, and go back to normal. Okay, so here's our standard normal distribution, right? So watch this. Remember the z-score was -1 that corresponded to 45? All right, whoops, -1. Okay, there it is. See? All right. Notice the probability is the same. That's what I mean about how we can take any normal distribution and transform it into this standard normal distribution by finding those z-scores. Okay, now like I said, right now it may be difficult to see exactly when you would need to do this. I can tell you right now you're going to have to use this relationship to solve question 25 in chapter 7. But we're also going to return to it in some future chapters. Okay, so I think you're going to find chapter 7 to be a lot easier than chapter 5. There's certainly fewer concepts to tackle. But go ahead and work the problems, and as before, try to do all of them, you know, and if you get hung up with one, skip it for the time being and then go back to it later. Always try and look at, you know, think of these things as some of them are like algebra problems where you have to sort of move things around to get the answer. And, you know, usually when you're doing algebra problems, you need relationships, kind of like this one. So maybe that one will help you out on some of those. And with that, we will end this video.